Morning, everyone. My name is Anil Subramani. I'm the General Manager, Enabling Futures Program for Amara Global. And I'm very pleased to welcome you to the first of our series of webinars on the power of positioning in the resources. And today we'll kick off with the first one, led by Frontier SI. I'd just like to introduce you to Amara first. I'll just wait for another 10 seconds to see if before we kick off. In the meantime, I'll get my my presentation on the screen. So if you could just bear with us. Can you all see that?
Anil, it's in presentation mode.
Sorry?
It's in presentation mode. You have to, or presenter mode, sorry, not in presentation mode.
Oh, okay. Is that better?
Perfect, thank you.
Lovely, thank you. As I said, welcome all to the first of the webinar series. I'll just introduce Amara very briefly before we kick off. Amara Global is a 60-year-old organization. We've been based in Australia, but we're a global organization. We're a not-for-profit, member-based company, and we go back in purpose to our original constitution, which is about enhancing the standing of the resources sector globally and in Australia, sustaining the development of the sector, and most importantly, ensuring that we deliver new data, knowledge, technologies, products and services to our members and to the community. Our operational mission is to create platforms where we can bring thought leadership that help address the issues and opportunities within the industry to ensure transformational change through pre-competitive research and development, which is both innovative and can be implemented. And so we focus very much on that pathway to implementation. One of the reasons for this workshop is to ensure that we keep an ear out and listen to what industry has to say about where the opportunities and challenges lie for research and development. Hence this workshop. What we'd like to get out of this workshop is, from these educational webinar series leading up to the final workshop on the 3rd of December, is to get from industry where the pain points are, where the interest is in future research and development in this particular area of endeavor, which is the power of positioning and the spatial sciences. And from there, we go on to ensure that these are addressed by researchers and by SMEs who provide the solutions for the sector. So without further ado, we'll get Chris Marshall, who's today's speaker, to talk to us about SBAS. Chris Marshall is a positioning engineer at Frontier SI, who has spent the last few years contributing towards the Australia-New Zealand SBAS following the completion of his master's degree in spatial systems engineering from the University of Melbourne. Chris has leveraged his keen interest in spatial information and positioning technologies to help evaluate the performance of the systems and promote the uptake of the forthcoming satellite infrastructure. So quite an exciting topic and technology that's going to be made available to everybody here in Australia and in New Zealand. The talk by Chris will be followed by a Q&A session. So please post your questions through the chat screens. And then once Chris has finished his presentation, I'll try and moderate the questions for Chris to answer. So without further ado, Chris, I hand over to you. Thank you.
Thank you very much, Anil. I'm glad to be here. I will just quickly share out my slides and I'll get this underway. Bear with me for a moment. All right, hopefully you can all see my slides at this point. Let me just bring up the correct window. Excellent. All right, so yeah, thank you all for attending today. I'm going to be speaking about the power positioning and resources, specifically in relation to SBAS, the test bed and the next steps. Might just quickly have a bit of a rundown of Frontier SI, who we are, and yeah, thanks for introducing me, Anil. So Frontier SI, we've spent the last 14 years or so as a CRC for spatial information. So following that 14-year stint as a CRC, we've rebranded to Frontier SI and we've continued that same sort of role. We sit somewhere between industry, government, and academia, and we try and bring forthcoming ideas from spatial and we push them through that pipeline, bring things to market that would otherwise be research-based. So there's a lot of innovation programs on the way at Frontier SI. Have a look at our website and you'll see some of the stuff we're about. Specifically, I'm going to be talking about the SBAS, the test bed, and the next steps and what that means for the resources sector today. As Anil mentioned, this is part of a bit of a program we've got going. So there's 3 webinars we got teed up over the next 3 weeks, all on the same time slot, so you all know when it's going to be. So this is the first webinar on SBAS, the test bed, and the next steps. Next week, we'll be joined by Geoscience Australia's Ryan Ruddick, who's going to be speaking to us about Positioning Australia, the program and services, which is in some way a higher precision counterpart to some of the SBAS I'll be talking about today. And then the week afterwards, we'll have Nicholas Brown from Geoscience Australia speaking about datums and reference frames, which we see as a very fundamental background information for having robust discussions around positioning and data, specifically as applied to industry. Culminating in the workshop on the 3rd of December, where we hope to get as many people along as we can to have some robust discussions around applying these sort of technologies and challenges in the resources industry. So make sure you come along to these set of webinars and you'll have all the tools you need to have a great discussion on the 3rd of December with the rest of us. Great, so without further ado, I'll just dive right in. So you might be wondering, what is SBAS? So the SBAS stands for Satellite-Based Augmentation System. It's basically a technology to improve the quality, accuracy, reliability, and availability of GPS positioning, or GNSS positioning, as it's more broadly described. It does so by supporting wide area regional augmentation through the use of satellite broadcast messages. So using the SBAS, you can achieve sub-meter positioning instantaneously. It does so by integrating measurements that are taken across a full network of continuously operating reference stations around Australia and New Zealand. These are ground stations that have been surveyed in, so they have a known location. And by observing the different satellites in current view, they can work out the difference between their known position and their recorded position from the services, work out correction factors, which are then sent via a geostationary satellite down to users who can then use those factors to correct for atmospheric errors and other common error sources. So the SBAS is not a new technology. The SBAS has been developed about 10 or 15 years ago now, and the first one was actually rolled out in the USA. So there's now actually regional systems in the USA, India, South Korea. There's one under development in China, I believe, and of course there's one in Japan as well. I might be missing one there, but bear with me. So in 2011, Australia first looked into the application of SBAS technologies and brought it to the government as a potential idea for infrastructure development. In the reviews, and sorry, New Zealand did something similar in 2014, in the reviews that they looked at that time, it was found that the sort of benefits that accrued mainly applied to aviation. So SBAS was initially an aviation technology. It was developed to allow safe landing of planes into aerodromes where they didn't have an instrument landing system, which is a quite expensive piece of ground-based infrastructure that has a whole bunch of different requirements for getting them set up and operating them in the future. So there's significant costs associated to rolling out instrument landing systems to regional airports and things like that. So SBAS was initially designed to fill that gap and allow precision guidance down to the runway. At the time of this initial investment, it was decided that SBAS would have to be part of a whole government approach, looking at all sectors, not just aviation, to make it worthwhile. So in late 2016, that's exactly what happened. Australia invested $12 million for a SBAS testbed demonstration, and New Zealand chipped in 2017 with an extra couple $1 million. So this project was then kicked off. It was a joint effort between Geoscience Australia, Land Information New Zealand. We had GMV as the SBAS providers. We had Inmarsat as the service provider on the satellite. FrontierSI ran the coordinated industry campaign, and Lockheed Martin ran the uplink station. So FrontierSI's role in this program was twofold. We coordinated the industry campaign, and we worked with an economics consultant in Ernst & Young, New Zealand, to model the economic benefits from the service and produce a set of reports, which I'll speak about a bit later on. So this SBAS testbed was a coordinated program of 27 demonstration projects across 10 sectors of industry. We engaged with over 150 organizations across all sectors, as I mentioned. So aviation, construction, maritime, utilities, rail, resources, road, spatial, agriculture, and consumer technologies. So each of these sectors was analyzed for various use cases that we could use SBAS for, and the ones that could be quantified were quantified to build up an economic benefits analysis. In some cases, there was technology demonstrators just done to prove whether something could be done. In other cases, we were quantifying what benefits would be accrued by doing so. So the SBAS itself, the way we've implemented it here in Australia is a little bit different to the way that the other SBASs around the world look. We've got something called the Generation 1 SBAS, which is only using GPS L1 frequencies. So without going into too much detail about specifically how these technologies work, this is the most basic signal correction that you can use for SBAS. So it's just augmenting one constellation of satellites over one particular signal. This is the same as the implementations around the rest of the world. I think almost every current SBAS in the that are currently operational in the world are only L1 SBAS. In our implementation from 2017 to 19 on the testbed, we actually had 2 more additional signals that were available for testing. We had a dual frequency multi-constellation SBAS, which corrects not just L1, but L5 frequencies as well, and on the GPS and Galileo satellites, the Galileo being the European constellation. So there's some work being done in Europe on high precision GNSS augmentation, which is sort of adjacent to this SBAS, but regardless, these first 2 technologies can be considered to be roughly similar in terms of achievable accuracy. Both will get you to that sub-meter level instantaneously. The difference is the dual frequency multi-constellation SBAS has some characteristics that could be beneficial in certain circumstances due to the fact that it's using multiple frequencies and multiple constellations. We also had this precise point positioning or PPP service available as part of the testbed. So this was a fundamentally different service. The first 2 are considered code-based, and this is a carrier-based solution. So what that means is that this PPP signal can actually get down to decimeter or 10 centimeter level accuracy, but it requires a convergence period to do so. So you'll turn on the receiver and you'll start getting positioning around that meter level, similar to SBAS L1 or DFMC. However, over 30 to 40 minutes after that time, as long as you have a good sky view and you don't obstruct the antenna, that positioning quality will go from meter level down to that decimeter level over time. So of course that unlocks a whole host of different applications and different use cases. So based on the technologies we demonstrated throughout the 27 demonstrator projects and engaging with 150 organizations from across industry, the big tagline numbers we came up with as part of the economic benefit analysis was a projected $7.6 billion value to the Australian and New Zealand economies over the next 30 years. It's important to note this is a 30-year projection. The major benefits accrued to the agriculture industries, the resources industry, the road industry, and the construction industry, all indicating over $1 billion of potential benefit in the next 30 years. So later on in this presentation, I'm going to dive a little bit more into the EY economic benefits as written in the report, and I'll go through some of the major use cases and the benefits as they apply to the resources sector. But first, why would you use SBAS? So, put simply, improve free-to-air positioning accuracy without requiring extra hardware. The best thing about the SBAS L1 service, being the most basic implementation of the service, is that you don't need any special hardware. A standard GNSS receiver can pick up the SBAS signal because it goes over the same frequencies as the standard GNSS observations that it'll be taking in that receiver, and it can theoretically, with this a software update or a quick patch, they can enable SBAS corrections on many, many devices. And there's actually a list on our Frontier Size website of the currently compatible SBAS receivers for Australia and New Zealand. By using the SBAS augmentation, you can get reduced errors in your collected data sets, which will improve the reliability compared to standalone GNSS. So if you were going to use standalone positioning for a certain task, by using SBAS, you'll get better results. And if you are able to leverage the PPP, you can get down to that decimeter level. So that next generation technology, there's a lot of work being done on PPP at the moment, and some in the academia is looking at furthering research to lower that convergence period from 30 or 40 minutes down to, in some instances, people are quoting, a matter of minutes, depending on how many signals you put into the technology. So depending on what that final implementation of PPP looks like, it may become easier and easier to use over time. So just to further illustrate some of these benefits of SBAS, I'll just describe a quick test that I did in this year, early on in Docklands near the Frontier SI office. So in this particular demonstration, I've taken two SBAS receivers. These are EOS Arrow 100 receivers, which are, I would consider them fairly good quality. They're not on the cheaper end of the spectrum, they're somewhere in the middle. And alongside that, we took a Septentrier Asterix SB receiver, which is actually, I'd consider a geodetic quality or very, very high quality GNSS antenna used for surveying purposes mostly. I put the three of them into a backpack and I connected them all via a passive signal splitter into an antenna, a Topcon G3A1 antenna, which is also quite good quality GNSS antenna. So by connecting them via a passive signal splitter, what that means is that the satellite observations at the antenna will be shared across all three receivers, and they'll all see the exact same sky view as if they were all individually connected. So the test environment was in a Docklands park, and I had this pole set up with a bipod, which I then used for a stationary positioning test and a walking positioning test. So I captured points, lines, and polygons simultaneously through all three receivers, which allows me to do second-by-second comparison of the reported position of each and post-processing of the reference trajectory to serve as a ground truth. I'll explain that more in just a moment. So the test one that I did was point averaging, where I set up this receiver over the corner of a concrete pad in the park, left it for a couple of minutes. The data from each receiver at each corner was then averaged to produce a polygon. The polygon area was then compared to figure out which one had the best accuracy assessment. The second test I did was a line capture test, where I walked this receiver setup along footpaths and defined edges around the park. And I took the data again, did post-processing, and compared the different results from each of the different receivers. So I then compared horizontal and vertical RMS, or root mean squared, calculated from the second-by-second errors at each receiver. So this is the point averaging test. So you can see this underlying white polygon with a black border on it. So that's the reference polygon that we've post-processed. So when I say post-processed, I mean that the high-quality geodetic antenna that I mentioned before, the Septentrier, that provides us with raw observations from the satellites. What we can do with those is take them back to the office, put them in surveying software, and we can get a solution out that has centimeter level accuracy. So it solves for all known error sources, uses that same cause network I mentioned before, and other online geodetic products to basically get down to a very high degree of accuracy. Because that reference polygon is a higher order of magnitude in terms of accuracy compared to the SBAS, we can make direct comparisons and use that ground truth as that reference polygon. So we compare the three. So first, if you have a look at this orange polygon, this is the EOS-R100 with the SBAS switched off. If you were to inspect the four corners of this rectangle as opposed to the reference polygon, you can see that each of those corners has some offset. This is due to the fact that over a couple of minutes, there's a bit of drift in the antenna position. So the antenna position stays rigid in the GNSS recorded position through each receiver. So the SBAS off receiver has positioned its corners a bit further away from the reference polygon than you might expect, in some cases up to ½ meter off. The accuracy, the area estimate for this region then from the Arrow 100 with SBAS off was about 14.5 meters. When the SBAS was switched on in the exact same circumstances with the exact same antenna, same observations at the same time, the same antenna, the same receiver kind, the EOS Arrow 100, with SBAS switched on, was able to get quite a lot closer to each of those four corners of the pad and resulted in a 15.9 meter estimate. So compared to the 16.4 actual area from the reference polygon, you can see there's a significant increase in the quality of that accuracy assessment from the EOS Arrow 100 with SBAS on as opposed to SBAS off. So by switching SBAS on, you can clearly get a better understanding of what the area of an interesting feature is using this approach. Here's another test. So this is a line capture test. So if we start in the top left part of this sort of map, you can see all three receivers start on this line quite well coupled, all in the same position. As a traverse happens going counterclockwise around this park, you'll see that the lines begin to diverge somewhat. SBAS off being the orange line, by the time it's made 3 or 4 corners and is in the northeast part of this picture, you can see there's offset of around 2.5, sometimes 2 or 3 meters. So as these turns occur, as the observation conditions change with the SBAS off, there is errors introduced into the results for that receiver. At the same time, on the same observation conditions, the same receiver kind with SBAS switched on managed to maintain a much better fix and stay much closer to that reference line throughout the full test. So the statistics in the center of the graph here show that throughout this short test session, which was about, I think it was 35 or 40 seconds of testing, so it's not a huge data set to look at, the SBAS off receiver managed a roughly 1 meter level accuracy horizontally and about 2.5 meters vertically. Now, I mentioned before, this is quite a good GNSS receiver. Usually you wouldn't expect those good results under that time with standalone positioning. However, in this short test, that's the positioning results we got, so it's quite good actually. However, with the SBAS switched on, the same exact kind of receiver was able to get down to a 20 centimeter horizontal positioning RMS with 1.2 meters vertical. So you can see there's a significant uplift in positioning accuracy when using the SBAS on as opposed to the same receivers with the SBAS off. And again, we use the same method here for the ground truth to make that underlying reference path. So if you're looking to understand a little bit more about some of these technical results and a bit more about the SBAS testbed, there's actually 3 reports available on the Frontier SI website. The one I mentioned a bit before, and I'll go into a bit more after this slide, is the EY Economic Benefits Report. So that's a report where you can have a look at not just the resources sector, but all sectors of industry. It's got a particular one-page, it's got a one-page upfront summary for each sector, which goes through the major benefits, how they accrue, what the values are, and what use cases they come from. So if you're looking for a bit of an overview and how this thing will apply to various sectors, have a look at the EY Economic Benefits Report. The project report is an overview of the SBAS testbed projects that were run by Frontier SI over the last few years, with a particular overview on each of the demonstration projects, who it was with, what they looked at, and what they were aiming to prove with their trials. There's also a technical report which describes some of the Frontier SI internal testing, some of the other work that was done to fill in the gaps in the SBAS testbed program to demonstrate other use cases, and a bit more technical detail. So I'm going to go through some of the technical benefits, sorry, not technical, the economic benefits rather, that were identified for the resources sector as part of the EY Economic Benefits Report. So the largest one was around $636 million projected over the next 30 years in operating expenditure savings associated with better material management, resulting in additional 64 million tons of iron ore able to be produced. So clearly the application here will allow increased productivity. So moving forward to haul trucks, there's a projected value of $577 million over the next 30 years in fuel and labor savings enabled by enabling the haul trucks to move faster and avoid incidents due to a more accurate collision avoidance systems, or CAS. there's a projected 23 million tons more iron ore production enabled through better shovel productivity, which can result in around $230 million of operating expenditure savings over that period. There's also around 205,000 hours of whole truck vehicle downtime avoided in an operational saving of $130 million present value over the next 30 years. So there was also a number of demonstration projects that were run as part of the SBAS testbed. This one was run with Queensland University of Technology and Wenco International Mining Systems. They were collaborating to conduct a series of field trials in Queensland. So they were demonstrating the use of SBAS services to V2X, or vehicle to everything safety, by conducting analysis of warnings between two vehicles in a range of collision scenarios. From that test project, they determined that SBAS would provide improvements to the solutions, particularly if you were using the PPP service, which would help in maintaining stable relative distances between objects while parking side by side, even under challenging environments, like you would find in a mine site. Similarly, they found that a rise-run matrix, which is commonly used in contract mining, the unaugmented GNSS or standalone GNSS was not good enough to allow them to directly use that for calculations of the rise and run matrix directly. So if you were to use SBAS augmented solutions, then that accuracy assessment would be significantly more accurate. It would be closer to the real value. And specifically, if you use PPP, they found that the RTK solution they were already using was of a comparable or similar quality, with differences less than 3% in the vertical axis, which is always, vertical is always a bit more difficult for GNSS systems compared to horizontal, just due to the nature of satellite geometry. One other demonstration project we ran part of the testbed was with Curtin University and Roy Hill Mines. So these experiments focused on usage in augmented reality, digital pegging, clearing, and autonomous operations on car and drill machines at the mine sites. So from all the SBAS-aided solutions that were available, it was confirmed that the PPP solutions would provide the best accuracy, and assuming that you could get that convergence period in there. As long as you start that convergence period early and you don't actually obstruct the antenna, you can basically maintain that level of accuracy for the full session. So based on their findings, Roy Hill is recommending that PPP solutions could be implemented in various mining applications, especially digital pegging, clearing, and autonomous operations in the future. So from the economic benefits report, we have identified these major economic benefits based on these use cases. So reduced collisions via enhanced collision avoidance systems, reductions in vehicle downtime, improvements to haul truck efficiency, enhanced exploratory survey efficiency, enhanced shovel productivity through enhanced ore mapping, improved plant operating efficiency through better material management, reductions in environmental incidents, improved loader and shovel availability, enhanced maintenance of vehicles and equipment, and of course, enhanced machine guidance. There's also a couple of benefits that were identified as part of the economic benefits activities, but couldn't be quantified due to various factors, including augmented reality management and the improvements to health and safety of workers via worker tracking. So the big remaining question is, when will SBAS be available for use? Unfortunately, there's a tender process underway with Geoscience Australia to provide the operational service. So the official announcements around the SBAS will come through Geoscience Australia. I encourage you to sign up to the Positioning Australia newsletter to get official word. The last announcements publicly were saying that SBAS signals are expected to become available for ground users once again in 2021. And the SBAS Safety of Life certification process will expected to be completed around 2025 following all regulatory approvals. That process for aviation use is going to take a little while longer. As I mentioned, there's a lot of regulatory process involved there. So yeah, sign up to Geoscience Australia and you'll get the latest on when we can expect the positioning services back online. So a little bit of looking forward to next week. There's a counterpart to this sort of SBAS technology. If you don't have SBAS and you do happen to be inside areas with internet and mobile coverage, there's the national positioning infrastructure, which can deliver you 3 to 5 centimeter services in near real time, as long as you can maintain that internet connection or that mobile data connection. So this is going to be spoken about in a bit more detail next week by Ryan Roddick from Geoscience Australia. So make sure to tune in if you'd like to hear a bit more about the high precision services. So between the application of the SBAS, so the L1 GNSS, the DFMC service, and the PPP service, and the NPI capabilities, being the RTK service through OzCores and that 3 to 5 centimeter service, as well as open cores data and open source software. Geoscience Australia's Positioning Australia program is looking to make it very simple for all users throughout Australia to leverage these signals, make them work for your particular application, and get down to those high precision applications that we all know are possible. So just another quick note here, Positioning Australia, Frontier SI is currently collaborating with Geoscience Australia and leading academics and industry experts to gather information on the positioning value chains across multiple industries. So we'll be reaching out to organizations to facilitate discussions around positioning needs, use cases, and the user requirements to help shape the delivery of the positioning services by the Australian government in the future. So if you would like your organization to be involved with those conversations and that process, feel free to reach out to Laurie Mansell or Dr. Ryan Keenan, who are involved in that process. If you don't reach out, you may be contacted at some point by someone from this group or Positioning Australia. By all means, your contributions are greatly appreciated, but your participation is highly optional, so you can opt out at any time. And yeah, thank you very much for listening to my presentation. If you'd like to find out a bit more about getting started using GNSS infrastructure in Australia and New Zealand, get in touch with the positioning team at Frontier SI. We'll talk you through the current state of things and provide you advice as it applies to your business, your application, and your use cases. Thank you very much for listening. I'm about 5 minutes early, so I have a little bit more time for Q&A.
Thank you, Chris. That was a very exciting presentation on what's a technology that's going to be so widely available, and that's really remarkable. Thank you also for focusing so much on the use cases and the work done within the resources sector. And obviously, I think it's limited by imagination where this technology can be put to use, and Frontier SI has already done a lot of that use case studies and testing, which shows the value that the mining industry has. There were a few questions. Can you tell us about some more about some of the challenging areas within the resources sector with the use of SBAS and how it can enhance use? You know, for example, you mentioned challenging environments in the mining sector, deep open pit mines, particularly with relation to the Z measurements, the Z-axis measurements, and how very often that's a real challenge. How will SBAS help in those such areas?
Thanks, Anil. Yeah, so GNSS technology is 100% tied to the observation conditions in terms of what accuracy you can expect to achieve. So the coupling of the hardware you've chosen, so the antenna, the receiver, and the environment that you're operating it in, those are really determine how much accuracy you can get out of the system, as well as, of course, what augmentation you're using, be that RTK, SBAS, or otherwise. So when you're talking about open pit mines or areas where you're significantly below the surface of the Earth, the problem arises that your sky view in what your antenna can see above it is more limited compared to being at ground level or in an open sky environment. So the more contracted that sky view is, the less observations you'll have for your GNSS position, so the worse the positioning accuracy will get. SBAS can help somewhat with those circumstances. When you have fewer satellites in your sky view, you can still use that SBAS augmentation to provide better accuracy. However, the SBAS is another satellite, so it does sit up in the sky at a particular elevation angle, in a particular orientation. And if that happens to be obstructed, you can actually not pick up the SBAS signals. So moving forward to 2025, when the SBAS Safety of Life Aviation service is available, there'll probably be 2 SBAS satellites available, which will start to solve that sort of issue. So if one's obstructed, theoretically the other one will still be visible. However, we're still going to be subject to those same limitations. If you're very, very close to a pit wall, if your antenna can't see the sky very well, or if you go underground at all, your observation conditions will suffer. Of course, if you go underground, you can't expect to get any GNSS positioning at all.
Thanks, Chris. Just going by that explanation you gave about observing conditions, pit wall, blocking signals and things like that. To what extent can SBAS replace current mine positioning technologies or infrastructure, because they are quite expensive? So if not entirely replaced because of what you just said, can they at least go some way towards making it a cheaper infrastructure or more cost effective?
Absolutely. So many mine sites might be currently using high precision GNSS such as RTK solutions or other augmentation systems. SBAS and the NPI capability with the RTK services there, they're provided for free to all users who wish to use them. That's obviously a large cost saving for some people. And of course, SBAS has the additional benefit that the hardware is much more readily available than RTK hardware. So in terms of barriers to entry, SBAS really does bring a lot of those barriers down. You can have access to higher positioning quality at lower costs than ever before, and it opens up a whole host of applications. That doesn't mean at all that the SBAS will replace the need for 3 to 5 centimeter positioning in certain applications, but that sort of service is also going to be made available through the NPI capabilities. So realistically, we see SBAS as a facilitator of new use cases. We can see it as a backup for existing use cases. And generally speaking, the barriers for using SBAS are significantly lower than they have been ever before. So the barriers for high precision data being used by organizations are just becoming easier over time, I think is the best way to put that. So yes, we don't necessarily see SBAS replacing all use cases, but it's definitely an option that should be looked at and could definitely replace many existing applications, specifically those where you're not currently using high precision GNSS.
Thanks, Chris. It certainly seems that particularly when the second phase, when it becomes compliant with the use in aviation, then it'll just increase the number of use cases which can rely on SBAS.
Yeah, absolutely. I think there won't be a significant performance difference when there's 2 SBAS satellites online. It's more of a redundancy thing. As you can appreciate, aviation sector is not 100% focused on the highest possible positioning accuracy. They're more worried about landing planes on runways. So you have a bit of a leeway there. In terms of aviation, they're more interested in integrity. So there's integrity messages as part of the SBAS service, which tell you roughly, as a ballpark, you are here plus minus a large amount. As long as that bounding region for the plane stays less than a certain limit, you can continue using the service. If it goes outside those limits, you're meant to stop using the service. So that's that particular component of the infrastructure is what's going to take that extra regulatory approval and take a bit more time to get off the ground.
Chris, thank you. I was going to ask you about, whether you had some more interesting applications of SBAS that were identified during your testbed, and I do want to add another part to that question. The mining industry makes extensive use of drones, and one of the most advanced uses of drones. Can SBAS technology be utilized by drones? Absolutely.
Yeah, there's absolutely nothing stopping your average drone from integrating an SBAS augmented solution in its GNSS component. I think many off-the-shelf drones actually have SBAS capable hardware on board. Whether or not they're locked down is maybe a manufacturer question. However, there was work done during the testbed, and there's continuously work being done to use SBAS for drones. Specifically, there's some discussion around whether or not the SBAS will give you a high enough level of accuracy to no longer require the use of ground control points, which you can then cut out some certain office-based tasks and use the data from the drone more directly in operations. Of course, the 3 to 5 centimeter service can definitely apply there as well, as long as you're within that service region.
Thanks, Chris.
The second part of that question about other particular use cases, I don't know, a fun one that came up during the test bed that I thought was really great was actually an agriculture one. Some people are looking at putting SBAS enabled collars on cows so they can use them for virtual fencing, they call it. So theoretically, you can have your cows in a field, have them lined up, and if they stray too far to a certain direction you don't wish them to go, the cows will get an auditory alarm or otherwise, and over time they can learn that that's not something they want to do. With the end goal of having all your cows lined up in a field, moving in a certain direction as a large sort of lawnmower situation, which I thought was a very interesting application.
Absolutely, that's brilliant. We had a question from Darren Wolford asking about haul trucks already using better positioning. How will a decimeter service improve that efficiency?
Sure. So PPP service is a bit different to existing RTK services. It doesn't have any data requirements. The PPP can be delivered completely from satellite. So in that way, you don't need the two-way communications from the haul truck back to internet services or otherwise. You just need a single way communication from the satellite down to the haul truck. Of course, there might be existing requirements around communications to send that back to a computer system or otherwise. However, the GNSS component there will be simpler. Yeah, that is definitely one of those applications where 3 to 5 centimeter service might be more applicable, and that's going to be provided for free for all users through the MPI. But SBAS definitely has some applications for some of those use cases. The auxiliary stuff, say the collision avoidance systems that might not be tied into the high precision services, they can definitely leverage these SBAS signals, and they can apply them, more cheaply and more widespread than could ever be done before.
Thank you. There is a follow-up question from Darren. I don't know whether you entirely answered it, and that's about what additional hardware being required or needed for the PPP, as it will not run on the current hardware.
So PPP is a bit more under development than the other sort of services. The DFMC and the L1 SBAS have had their ICDs or interface documents available for a while now, so manufacturers know exactly how that's going to be implemented. There is some questions at the moment around how the PPP service will be implemented, because it's I hesitate to use the word bleeding edge, but the applications here, as shown of the Australian SBAS testbed, they haven't been tested elsewhere in the world. They haven't really got satellite delivered PPP available to everyone across the country for free as well. So in terms of what that will finally look like in its final implementation, it's hard to say at the moment. However, it may be required to have a more specialized hardware to get PPP. However, the SBAS L1 will be available through many off-the-shelf receivers presently.
Okay, thank you. As a final question there, Chris, thank you so much for your presentation. What excites you most about being part of this rollout of this new technology across 2 countries?
That's a great question. I'm through all of the engagement and through all these testbed projects, I think it's just been amazing for me personally to just put my mind into various industry applications and really look at the breadth of how these things can really be applied. I mean, positioning technology is becoming way more ubiquitous these days. It's being applied for a whole host of tasks that it's never been applied to before. The spatial, so the spatial sciences are really intersecting with all other aspects of industry in ways they never have before. So moving forward, the positioning technology is going to become more and more and more important to all kinds of different applications. So with that in mind, I'm really excited to see how the general public and various organizations are going to take these services, which are going to be available for free and going to be, greatly beneficial for many use cases. I think the industry has always been really good at innovating and coming up with new ideas based on what's available to them. So I'm really excited just to see once the SBAS is up and running, how is that going to be applied? Who's going to be using it, and where we're going to see things that we've never thought of before. We do our best to, get across all current use cases and ways that it's currently being used in the industry, but realistically, innovating and going forward, there's going to be so many things we've never even considered.
Thank you very much. I think we will call a close to the webinar now. Before we go, I'd like to thank Chris, Eldar, and Nick from Frontier SI for the effort that's been put into getting these webinar series up and running. Thank you all for that. I'd also like to thank Sarah and Imran in particular for helping organize the series and the workshop. We look forward to the audience participating in the remainder of the 2 webinars. The next one is on the 19th of November at the same time. We look forward to seeing you there. Please let your colleagues and friends know if they're interested in these topics. The next one is, as Chris has already mentioned, focused on the talk by Geoscience Australia. And we really do look forward to seeing you all back here next Thursday. Hope you have a lovely day, and see you later. Thanks for attending.
Thanks everyone for coming.